So in this final video of the lecture, we're going to talk a little bit about the role of engineering drawings within the engineering design process. So why drawings? Well, when you think about that, remember that us as humans, if we were to look at our brain, about half of the actual gray matter is dedicated to processing visual images. You've heard the term that a picture is worth 1,000 words. Individuals just naturally interpret things better when they're presented in graphical form versus actual written form. So it's not surprising that when engineers actually create things, that they want to convey that information in the form of a drawing. Now, there's lots of different drawings that add value within engineering workflows. They vary with respect to what they contain, along with their complexity. And we're going to kind of look at a taxonomy or model for kind of classifying them later, but they vary all the way from things that you sketch by hand to 3D CAD models. When you think about the value of a sketch, you're really talking about something that you're creating in a time-constrained environment. Maybe an idea comes to your mind and you just want to capture it, or you're trying to describe something to some other engineer and the words just aren't doing it. Having the capability to kind of reflect certain aesthetic properties of your design using hand sketching is incredibly valuable still, even in the age of computer-based drafting or CAD, as we'll see in a minute. When you think about a technical drawing, really the type of technical drawings that exist from an engineering design point of view vary depending upon the desired application along with the discipline. Mechanical engineers, you're routinely generating two-dimensional drawings of parts or assemblies. Civil engineers are making plot plans, or they're making actually plans for building construction and so on. Electrical engineers, we've already looked at schematics in this class when we've worked within Multisim. They just reflect the interconnectivity electrically between components. But in addition, if you're actually putting those onto a printed circuit board or a PCB for a final product, you might use a drawing to show how the various parts are laid out and how the connections are routed. So when you compare the actual three types of kind of engineering drawings that we'll talk about, on the left, we have a hand sketch. Notice that it looks like something I drew. It's not very good, but it reflects some key kind of aesthetic characteristics of the different elements of the drawing. And in hand sketching, you're always kind of adding a little bit of text markup. That way people can kind of interpret your bad drawing and know exactly what you're talking about. In the middle, we have what you would call a plot or a print. It's kind of reflective of engineering design 20 to 30 years ago. And still useful today, though, if you're going to manufacture anything by hand in a machine shop or something like that, or if you're trying to support inspection or quality assurance workflows, these types of drawings you're going to see them all the time. And their format is actually standardized by either ASME or ISO, depending on what standard you're working with. Around the outside, you have these zones, these kind of like a spreadsheet, these numerical and alphabetical identifiers that divide the drawing space up into little grids, and you can point to them. You have text information contained within blocks, and then you actually have the drawings and dimensions these are particularly called orthographic projections, and they're meant to provide a distortionless view of the actual dimensions of the part. That way, if someone were to give this to you and say, hey, here's the drawing for this part, here's the actual part, is it right? You could take certain characteristic dimensions and kind of assess the quality. On the right, you have a 3D model. This is something that could interface automatically with a 3D printer. And obviously, when you look at that, it's very natural to us because it's rendered in kind of a perspective. That drawing rendering is called perspective. I guess a perspective projection would be the way that you would refer to it. And it's naturally drawn in a way that kind of mimics the way that photons hit the back of our retina and that we perceive three-dimensional space. So long story short, it gives the illusion of 3D versus an orthographic projection is meant not to distort and give an illusion of 3D. So when you think about textbook definitions of CAD software, so CAD is just computer-aided drawings. Anything that we're generating on the right there, where we're actually leveraging a computer to produce nice drawings that are useful for different applications. Usually people talk about CAD software as going into two buckets, 2D CAD and 3D CAD, but note that that's a misnomer. Even your most common native 2D package, AutoCAD, has some 3D functionality that's been added on. In addition, and more importantly, all of your 3D software can be used to generate those 2D drawings that we looked at in the middle automatically. So some names that you want to be familiar with as you kind of move on through your engineering career. 3D CAD software really is either made by an Autodesk product, and these are the commercial software packages. There's tons of freeware online like Onshape and Blender and whatnot that you might want to look into. But Autodesk is a big commercial manufacturer. The two products within engineering that are the most common are AutoCAD. That's a native 2D software package that's used for generating drawings. It has a lot of market share in civil engineering. and Inventor. And Inventor is a native 3D modeling tool that's useful for kind of engineering design workflows for product manufacturing, so common amongst mechanical engineers. SolidWorks is not made by Autodesk. It's made by a French company. It's also very useful for 3D modeling, computer-aided engineering, and interfacing with 3D printers. More recently, Autodesk makes a software package called Fusion 360 that's more of a direct competitor to SolidWorks. It's a little bit lighter weight and doesn't have all of that computer-aided engineering for manufacturing integrated into it. So other acronyms that you want to have heard of before, CAM or computer-aided manufacturing, you're just talking about any process where you're kind of inputting the dimensions of the product into a computer and controlling the manufacturing process according to those dimensions. In addition, CAE, computer-aided engineering, that's just any time that within your CAD you have additional analysis functionality added on, maybe something like finite element, which is just a numerical method that's added to kind of assess the structural integrity of a product. But one of the things I really wanted you to know is if you think about, I have to learn to use AutoCAD in order to generate these kinds of drawings, that's not true. If you just learn a 3D modeling software, you'll have the capability to generate those automatically. So why is it worth your time, maybe over break, to think about learning 3D CAD skills in more detail? Well, there's two big market trends that are going on right now that are really making these skills more and more valuable. One is just the prevalence of 3D printing, both on the hobbyist level, for prototyping. And when I say hobbyist, I don't necessarily just mean you in your garage. It could be a company and you're doing internal research and development and you just want to print up a quick prototype. 3D printing is becoming more and more prevalent. And those actual 3D printers, they interface automatically with these 3D CAD packages. So if you can draw in 3D CAD and you have access to a 3D printer, you can get a prototype up and running very, very quickly. In addition, 3D printing is becoming more and more valid from a commercial point of view, particularly in applications where you don't have scale. So we've looked at a lot of different applications this semester in the smart prosthetic space where you're printing one prosthetic for one person and it's custom. If you don't have scale, 3D printing makes a lot of sense. So the more and more that 3D printing becomes integrated within our daily lives, the more valuable it's going to be to know how to actually do 3D CAD modeling. In addition, another thing to keep in mind is the metaverse. So as more and more augmented and virtual reality apps come online, which are collectively called the metaverse, it turns out that the skills that are needed to draw in 3D using like SolidWorks and Fusion 360 generalize very well to three-dimensional game design development platforms like Blender, which can actually be used to develop these type of metaverse applications. So nothing wrong with spending some time to learn some 3D modeling. In addition, I just wanted to make sure that you were familiar with this term called a digital twin. If you've noticed, I've tried my best to really integrate a lot of emerging technology trends within the course. We talked about the Internet of Things, and we talked about artificial intelligence and data science and so on. So one of the terms that you definitely want to know is this idea of a digital twin. So this video will link out to a very quick talk by NVIDIA. NVIDIA is just a company that makes graphical processing units or GPUs. They do a lot of other stuff as well. But they're going to talk about how 3D modeling can be used to create these things called digital twins, which can really be used to improve the performance of an Amazon warehouse. So after you watch it, think about like what exactly is a digital twin of a physical object? Is it just a 3D model? Does it just look like the physical thing? Does it just have the dimensions? How does that differ from a basic CAD model? And in addition, think about if in the environment around you, if you could create digital twins of everything, what could you do from a business and engineering perspective? Why would you invest in actually developing digital twins of everything in terms of simulation and optimization? So it should be pretty clear from that video. But if you have any questions, just let me know. So I hope that this was a good kind of introduction to engineering design to fulfill one of our last course objectives. We're going to be doing a basic engineering design project in Teams at the beginning of next week. So I might actually bring it up in an actual announcement, but it shouldn't take too long. I intentionally, part of the theme of this lecture, if you notice, was accelerating to action because you're always going to fail. So part of the test really is just to only give you a little bit of time to come up with a design and kind of get some peer feedback and see what they think. So I will see you all next week. Have a great break, and I'll talk to you soon.